So for section 5.1, we're going to start looking at area underneath the curve. And to kind of set the tone for this, I want to look at a couple examples that are pretty practical and very applied. First one is how many coronavirus cases we experienced a year ago when the outbreaks first started. So this data is data from Michigan, and it shows you what was happening in terms of the number of new cases per day for the first 50 days. Now, if you use statistics, you can calculate a nice curve to kind of approximate this. So that would look roughly like that. But the place I'm going here is that I want to find the area underneath this curve. Now we can do this with calculus. And the area underneath this curve, assuming that this is the rate of new infections per day, the total area is going to represent how many total cases we have through 50 days. So if we move this slider a little bit, you can see it tracing out the area. And underneath here, let me scroll down a bit. That's the total number of cases. Now, when I did this last year, I think this number was within like a dozen or so of the actual total number of cases. So it's a really good approximation, even though this curve isn't really spot on with the number of new cases per day. Let me move this discussion over to the problem that you're going to work on. It's an area problem that corresponds to an old friend of yours, distance equals rate times time. So maybe you can go over this one. That would be a little bit better. So suppose you're driving in a car holding a steady 180 miles an hour for 60 seconds. How far would you go? Well, hopefully you remember a little bit about distance equals rate times time. Here's your rate. Time is 60 seconds, but if I want to work with it in this problem, I need to have it in units of hours. So what you could realize is that there's 1 hour has 3,600 seconds. And the nice thing about this is that by multiplying effectively by 1 here, this ratio is just a fancy name for 1. And multiplying by 1 like that, the units that I want to get rid of disappear, seconds, and I'm left with 60 over 60, or basically 1/60th of an hour, which makes sense. 1 minute is 1/60th of an hour. Putting that together, distance equals rate times time, that's going to be 180 times 1/60. It's going to be 3, and the units are going to be miles. Nice. Now, it's very unlikely that if you're driving a race car at 180 miles an hour, that you maintain that perfectly even for any length of time. In fact, the problem that we have is that that speed is not maintained for any particular length of time. It varies. So let's take a look at the actual data that we have here. There we go. And I fit a curve through that data. Now, it's not perfect, but it's going to be good enough for our purposes. How far this person travels during that 60 seconds is going to, again, be an area. Now, you can think of the area for our first problem with how far this thing travels as, again, an area problem. Distance equals rate times time. It's just the area underneath this curve. So the same thing down here. The area underneath this curve is going to be how far this car travels in 60 seconds. So not surprisingly, we're going to go over to Desmos and take a look at things there. And let's see. That's this one right here. Now, I've provided you a link to this site. So here's the data. And we can scroll down a little bit. I've got a curve that I fit to this data. So it looks like that. Now, we're only going to work with the data for the first 60 seconds. So if you want to switch and just use this curve, where I cut things off after 60 seconds, that's fine. It works either way. Now to get the area underneath this curve, we're going to approximate this area in a total of 3 different ways. The first way is you're going to take this slider and move it from left to right. And ready? Ooh, that's pretty cool. And notice that it sketches out a bunch of rectangles. What you're going to do is find the area for each one of these rectangles, add up those areas, and then get an estimate of how far the car traveled. Now it's just an estimate, right? Because as you can see, these rectangles aren't a perfect approximation of the area. In fact, over here, it's kind of bad. Now this is called a left-hand approximation because we're using the left-hand endpoint to get the heights of each rectangle. Left-hand endpoint of this interval, left-hand endpoint of this interval. Now, when it comes time to actually finding the area of these things, you can just click right here and it'll show you the height, you know, the width. So 10 times 168, etc. You can find the area. Now that's one way, is using the left-hand endpoint to get the height of these rectangles. Let's back this down. You can also use the right-hand endpoint. That's a different approach. So there. And you're going to get a different estimate. Now notice here using the right-hand endpoint, there's a pretty big gap here. So over here, you've underestimated, and you might want to look at what's happening in terms of underestimate and overestimate when the function's increasing and decreasing. That's going to be part of your problem. Now, if you wanted to, we could find kind of a third method, and I ask you about this in the homework. If we dial this up to, say, 5, and this one, let's just put it 5 as well. It's kind of a third method, sort of a hybrid. But that's a little hint at one of the answers to your homework. Let's see. Now, when you first calculate the area or your estimate of the area underneath this curve, don't forget that this is in seconds, and that to get things to work out, you should be dividing by 3,600 to convert seconds to units of hours, and then they should work out. Keep in mind that this car should go no more than 3 miles during that time. So if you're getting something over 3 miles, you're doing something wrong. I asked you about overestimate and underestimate. You should be able to look at the graphs and decide when the function's increasing, that a left-hand endpoint or a right-hand endpoint is going to be an overestimate or underestimate, etc. The answers you get from problems 1 and 2, I want you to average those and see which one looks the best compared to the real answer. Now, what's the real answer? Well, let's go back to this right here. Let me dial these down to 0. For what I consider the real answer, you can go down to this slider right here and keep an eye on things. If you zoom out or run the slider through all 60 seconds, we'll get an estimate of about 2.3877. So that's our estimate of the true answer. And I want you to compare things to the true answer and see which method was the best. The left-hand endpoint, the right-hand endpoint, or the average. So there's 3 estimates you should come up with. Which one of them is actually the closest? Then think a little bit beyond this assignment and say, well, how could you improve that estimate? And I gave you a hint when I set both sliders to 5. Wrap it up with giving me some feedback on the assignments, and you should be all set. Good luck.